Okay, so now I have a very dramatic scenario. I don't want you to be too frightened, but that's supposed to be Khaleesi. And here is the devious torture that she has been subjected to. So we're looking down from the top, and there is this rod that's fairly light and rigid, and on the end of it is a heavy mass. And it's rotating around, so this vertical axis at angular velocity omega naught. Khaleesi is right over here, and right in the path of this death mass. And so she's toast unless we can manage to slow it down to half omega naught. So is it true? I don't know anything about Khaleesi. Is it true that she has a dragon?
She has 3.
Okay, fine. So this dragon, as it turns out, packs a wallop. Okay, even though that's a big mass, this dragon is 4 times as massive. And so Khaleesi summons the dragon, and the dragon just drops down and grabs on to the bar. Okay? Everyone clear on what the dragon is doing? So I have a question for you. Okay, now I won't normally humor you by putting linear. I'll just use momentum, but because we're just learning that there's a difference, linear momentum conserved from the instant before the collision when the dragon grabs a hold of the bar to the instant after. 67% of you said linear momentum is conserved. 26% of you said that it's not, and 5 of you bought a vowel, so I guess that covers each of the vowels if we spread those out. And I'm not sure what the price was. Okay, so can I hear an argument why momentum is conserved? That seems to be the majority view. Yeah?
Just the collision, and momentum is conserved in collisions, and even though it's rotating, like the acceleration towards the center is not going to be relevant to the so short of a time.
Okay, let me see if I can summarize all that. It's just a collision. Momentum is conserved in collisions, and even though...
well, it's like it's rotating, so it's accelerating towards the center.
Even though it's rotating and accelerating towards the center...
it doesn't matter because it's a very short time period.
Doesn't matter because it's a short time. Is that, in general, what people agree on? Some people didn't agree on that. Some people said no. Who said no? Some brave no soul. Okay, fine. Some timid no soul. No? No soul. You are soulless people. No? So when is momentum conserved? And if you tell me always, I'm going to do a demo. Oh, wait, let me do it again. With chocolate this time. Let's see if it works. When is momentum... Damn it. You're supposed to stay.
When there's no external.
So, are there any external forces on... Oh, wait a second. What's the system? What's the system? So we have... This is a dragon. Yeah, that's a terrible dragon, but too bad. Okay? Top view. What are the forces on... What's the system? Ellie, what are you taking for your system?
I was stretching.
I know.
Let's say the system is the mass M and the rod.
The mass M and the rod. M rod. Not a rod, but M rod. And so the dragon is not part of your system. Is that right, Ellie?
I think so.
Well, it's your system, so you can define it how you like. Ellie doesn't want the dragon in her system. Then whatever force the dragon supplies is an external force, right? So therefore what? Right. So is linear momentum conserved? Linear momentum of what? Of what? What has any linear momentum here? Is there any linear momentum?
I mean, technically, you could say that M over a very, very short time period has a linear momentum in a particular direction, but then that direction is constantly changing.
He says that technically you can say that, I'm going to just draw it that way, that the momentum of mass m is that way, but it's constantly changing. Okay, the fact that it's changing direction doesn't mean that it isn't real or it isn't there. Okay, if it's moving with a velocity, does it have a velocity? Harry, does it have a velocity? Definitely. Okay, so Harry says it definitely has a velocity, which I might also decorate with V. Then multiplying by the mass, which it also has, would be sufficient to produce a momentum. So yeah, it has momentum. The question is that momentum going to stay the same when the dragon hops aboard? Yeah.
Well, you can ignore the external forces because force is dp dt, and if you model the collision as instantaneous,
Yep. Okay. So F is dp dt. And so if, I think we need to do this as a demo. I don't have a dragon handy, but I have a mass handy. Okay, so I need another volunteer. Alex. Okay, so we're going to set Alex spinning, and not too fast probably, because I'm going to hand you the mass. And you're supposed to not drop it on my foot. Okay, so you can spin a little bit and then reach out and take the mass. Don't pull it in, dude. Try it again. Okay, so yeah, this is, you got muscles. I want you to, yeah, hold it out. Perfect. That was, all right, yeah, we did. But we didn't drop the baton. That's pretty good. Okay, here we go. Okay, so was the linear momentum of his hand preserved in the collision? Not so much. All right, let's think about this collision. Where are there external forces? I'm going to enlarge, Ellie, the system to include the dragon, because if I don't do that, then forces that the dragon's talons exert on the rod are now external, and those are complicated, and I don't want to deal with them. So I want to make the dragon part of the system. So if I do that, initially, does the dragon have any angular momentum? No, not moving. And so is angular momentum, well, we'll get to that in a second. But now that those forces are gone because they're internal, I need to know what other forces are there on this system.
Does the dragon have his wings out or folded on his back?
Quiet, you. Yeah. Something is making it rotate. Something is keeping it in motion. Okay, what's that something? Quick, I'm going to throw up. Huh? Where? Ugh, I shouldn't have done that. Huh? So, is there gravity? Sure. Okay, which way? Into the board, right? Okay. So this thing must be falling down. under the force of gravity, right? Because there's no force on it to counteract that. Is that right? What's holding it up? The rod. What's holding the rod up? The rod's part of my system. Yeah, there's some kind of goofy hinge here that's holding it up. Is that hinge providing an external force? The rod and the hinge are part of the system. If nothing is holding the hinge up, what do you think is going... Okay, more demo. No, I don't have a huge rod out here. I can go back to the bag. When things in a gravitational field are let go, unlike in the cartoons, Ian, they fall, okay? So if there is no upward force here, there is a force of gravity into the board on this mass. So unless there's an upward force on this system, it will fall. But it ain't falling. So there is an upward force on the system. So I now have to be very nervous to inquire whether any forces here could be enough to mess up conservation of momentum. In fact, when the dragon plops on here, is that going to try to speed up the rotation or slow it down? Slow it down. And so there will be forces internally here. If the pivot does not counteract with appropriate forces, this point will move away from the fixed axis that it has right before the collision. So unless we can argue that, well, those forces are negligible because the collision is short, then we can't say that momentum is conserved. In fact, the dragon will do nothing to save Khaleesi, whatever her name is. Right, like I said, unless hopping on slows down the rod. Now, is the angular momentum about this point conserved in the collision? Because all the forces now between the dragon and the rod are internal. So they come in equal and opposite pairs. They don't change the angular momentum. So have we now increased the mass that's going round? So just like before, when I hand him the dumbbell, the angular velocity must go down to compensate. So if the angular velocity went down, the velocity went down. So momentum is not conserved unless there's no external force. Now, in a collision, you may argue, yeah, there's gravity during the collision, but that's not important because it's a modest force and the time of the collision is so short that it's not going to produce a significant change in momentum. That is, I can take this expression and say dP is about equal to F, well, equals F dt. And so if the collision time is very short, then the change in the momentum caused by a force that stays modest can be neglected. But we would have to argue that the pivot doesn't react strongly in order to keep this end fixed. But in fact, it does. So we can't conclude that, whoops, do I have, no. Wait, what happened? Oh, I lost my dragon. Okay, so in fact, we better calculate. So if the angular momentum is conserved, what was the initial angular momentum? L naught was equal to, okay, I got to remind you, moment of inertia is the sum over I of mi r sub I squared. And the angular momentum is I times omega. So what's the initial angular momentum? Well, that will be m d squared, because d is the distance away from the axis, and omega naught is the initial angular velocity. After the dragon settles, L final, okay, now angular momentum, the moment of inertia gets more complicated. We have m d squared still, that mass is still out there, but we have to add the moment of inertia of the dragon. The dragon is only at d over 2, so I get plus 4m times d over 2 squared times omega. And by conservation of angular momentum, we get md squared omega naught is equal to anything common over there. Yeah, I think so. So this is md squared plus md squared omega. So we can just wipe out all the md squareds, and we get that omega naught is twice omega, or omega is equal to 1/2. So the dragon manages to slow the rod down to half the angular velocity by landing halfway out.